Genomics and its application in health and agriculture, including the gene therapy. Genomics, the rapid progress in genome science and a glimpse into its potential application has spurred observers to predict that the biology will be the foremost science of the 21st century. Technology and the resource generated by the Human Genome Project and other genomics research are already having a major impact on research across the life science. The term genomics was coined by Thomas H. Roderick in 1987 for mapping and sequencing to analyze the structure and organization of genome. It includes sequence of genome determination of a complete set of a protein encoded by an organism and functioning of gene and metabolic pathway in an organism. Thus, genomics not only deals with the determination of genetic information present in an organism but also with understanding the mechanism by which this information is used by the organism. The genomics can be divided into two domains. One, the structural genomics. It includes one, construction of high resolution genetic and physical maps. Two, sequencing of genome. 3. Determination of the complete set of protein in an organism. 2. Functional genomics. It deals with the study of a functioning of genes and a metabolic pathway, that is, the gene expressed pattern in organism. The role of genomics in health. 1. Improved diagnosis of a disease. 2. Earlier detection of a genetic predisposition to disease. 3. Rational drug design for gene therapy and control system for drug. And 5. Pharmacogenomics, custom drugs. The technology and resource promotes by the Human Genome Projects are starting to have a profound impact on biomedical research and promise to revolutionize the wider spectrum of biological research and clinical medicine. Increasingly, the detailed genome map have aided research seeking the gene associated with the dozens of genetic conditions, including the monotonic dystrophy, fragile X syndrome, neurofibromatosis type 1 and 2, inherent colon cancer, Alzheimer's disease, and familial breast cancer. On the horizon is a new era of molecular medicine characterized less by treating the symptoms and more by looking to the most fundamental cause of a disease. The rapid and more specific diagnostic test will have possible early treatment of countless maladies. The medical researchers also will be able to devise novel therapeutic regimens based on new classes of drugs. The immunotherapy techniques avoidance of environmental conditions that may trigger the disease and possible augment or even replacement of defective genes through gene therapy. Application of genomics in agriculture. 1. Disease, insect and drought resistant crops. 2. Healthier, more productive disease resistance farm animals. 3. More nutritious product. 4. Biopesticides. 5th, edible vaccines incorporated into the food product. 6. New environmental cleanup uses for plant like tobacco. Understanding plant and animal genomes will allow us to create stronger, more disease-resistant plants and animals, reducing the cost of agriculture and providing the consumers with more nutrition. The pesticide-free foods. Already, growers are using bioengineered seed to grow insect and drought-resistant crops that requires little or no pesticide. The farmers have been able to increases outputs and reduces waste because the crops and herds are healthier. alternate use for crops such as tobacco have been found. One researcher has genetically engineered tobacco plant in his laboratory to produce a bacterial enzyme that breaks down explosives such as TNT and dinitroglycerin, waste that would take centuries to break down in the soil can be cleaned up by simply growing these special plants in the polluted area. Gene therapy, which are carried on chromosomes are the basic principles and fundamental units of heredity. Genes are specific sequences of bases that encodes instructions to how to make proteins. When genes are altered so that the encoded proteins are unable to carry out their normal functions, the genetic disorder can result. The gene therapy is a technique for correcting defective genes by the insertion, alteration, or removal of genes within an individual cells and biological tissues to treat disease. The researchers may use one of the several approaches for correcting faulty genes. One, a normal gene may be inserted into a non-specific location within the genome to replace a non-functional gene. This approach is most common. Two, an abnormal gene would be swapped for a normal gene through homologous recombinations. Three, the abnormal gene could be repaired through a selective reverse mutations, which returns the gene to its normal functions. 4, the regulation, the degree to which a gene is turned on or off of gene could be altered. Basic process of gene therapy. Several approaches to gene therapy are being tested includes one, replacing a mutated gene that causes a disease with a healthy copy of the gene. Two, inactivating or knocking out a mutated gene that is functioning improperly. Three, introducing a new gene into the body to help fight a disease. In general, a gene cannot be directly inserted into a person's cells. A carrier molecule called a vector must be used to deliver the therapeutic gene to the patient target cell. The vector system can be divided into viral vector, non-viral vector. One, viral vector. Currently, the most common type of vector is viruses that has been genetically altered to carry out the normal human DNA. The viruses has evolved a way of encapsulating and delivering their gene to human cell in a pathogenic manner. The scientists have tried to harness this ability by manipulating the viral genome to remove disease causing genes and insert therapeutic ones. The target cells such as the patient's liver or lung cells are infected with the vector. The vector then unloaded its genetic material containing the therapeutic human gene into the target cell. The generation of a functional uh, the generation of a functional protein product from the therapeutic gene restores the target cells to a normal state. Some of the different types of viruses are used as a gene therapy vector. Retroviruses, a class of viruses that can create a double-stranded DNA copies of their original genome. These copies of the genome can be integrated into the chromosomes of the host cells. The human immune viruses (HIV) is a retrovirus. One of the problem of gene therapy using the retroviruses is that the integrase enzymes can insert the genetic material of the viruses in any arbitrary positions in the genome of the host. If the genetic material happen to be inserted in the middle of one of the original gene of host cells, this gene will be disrupted. Insertional mutagenesis. If the gene happens to be one regulating solution. This gene will be disrupted insertional mutagenesis. If the gene happen to be one regulating solutions, the uncontrolled solutions, that is cancer, can occur. This problem has recently begun to be addressed by utilizing zinc finger nuclease or by including the certain sequences such as the beta globulin locus control region to direct the site of integration to specific chromosome site. The gene therapy trials to treat severe combined immunodeficiency (SCAD) were halted or restricted in the USA when the leukemia was reported in 3 of 11 patients treated with French X-linked SCAD, SCAD gene therapy trial. Uh, 10 XCID patients treated in England have not presented leukemia to date and have had a similar success in the immune reconstitutions. The gene therapy trial to treat the SCID due to deficiency of adenosine deaminase ADA enzyme continues with relative successes in the USA, Italy, and Japan. B. Adenoviruses, a class of viruses with a double-stranded DNA genome that causes respiratory, intestinal, and eye infection in human. The viruses that causes the human cold is an adenovirus. In September 1999, the gene therapy research community was altered to report of death of a man encontrolled in the gene transfer trial at the University of Penis, Pennsylvania. The Recombination DNA Advisory Committee (RAC) has published a review which involves a discussion of preclinical safety data, the design of a protocol, the informed consented document, and any overarching scientific safety or ethical issues relevant to the specific protocol. The review entitled Assessment of Adenovirus Vector Safety and Toxicity report of the National Institute of Health Recombinant DNA Advisory Committee was published in Human Gene Therapy in 2002. C. Adeno-associated viruses, a class of small single-stranded DNA viruses that can insert their genetic material at the specific site on chromosomal 19. Herpes simplex virus is a class of double-stranded DNA viruses that infects a cell type neuron. Cell types neuron. The herpes simplex virus type 1 is a common human pathogen that causes a common sore. The herpes viruses are currently used as a gene transfer vector due to their specific advantages over other viral vectors. Among the unique features of herpes simplex virus derived vectors are the very high transgenic capacity of viruses particles, allowing to carry long sequences of foreign DNA. The genetic complexity of the virus genomes, allowing to generate many different types of attenuated vectors possessing oncolytic activity, and the ability of herpes simplex virus vectors to invade and establish lifelong non-toxic latent infection in neurons from sensory ganglia, from where the trans genes can be strongly and long-term expressions. The three different classes of vectors can be derived from herpes simplex virus. The replication competent attenuated vectors, replication incompetent recombinant vectors, and defective helper dependent vectors known as amplicons. The replication defective HSV vectors are made by deletion of one or more immediate early genes. Example ICP4, which is then provided in trans by complementing cell lines. Lentiviral vectors. The lentiviruses is characterized by a long incubation period. The lentiviruses can deliver a significant amount of genetic information into the DNA of the host cells. So they are one of the most efficient method of gene delivery vectors. The HIV, SIV, and FIV are all examples of lentiviruses. The lentivirus is primarily a research tool used to introduce a gene product into vitro system or animal model. A large scale collaboration efforts are underway to use lentiviruses to block the expression of a specific gene using the RNA interference technology in high thorough format. The expressions of short hairpin RNA, shRNA, reduces the expressions of a specific gene, thus allowing the researcher to examine the necessity and the effects of a given gene in a model studies. These studies can be a precursor to the development of novel drugs, which aims to block a gene products to treat a disease. Another common application is to use a lentivirus to introduce a new gene into the human or animal cells. For example, the model of mouse hemophilia is corrected by expression wild type platelet factor 8. The gene that is mutated is human hemophilia. The antiviral infections has advantages over other gene therapy methods, including the high efficiency infections of dividing and non-dividing cells, long-term stable expressions of transgenes and low immunogenicity. Lentiviruses have also been successfully used for transfections of diabetic mice with the gene including FDGF, platelet-derived growth factors, a therapy being considered for use in humans. These treatments, like most current gene therapy experiments, show a promise but are yet to be established as safe and effective in controlled human studies. A viral protein involved in early stages of replications includes reverse transcriptase and integrase. The reverse transcriptase RT is a virally encoded RNA-dependent DNA polymerase. The enzyme uses the viral RNA genome as a template for synthesis of a complementary DNA copy. The reverse transcriptase also the RNase H activity for destructions of RNA template. The integrase ion binds both the viral chromosomal DNA generated by the reverse transcriptase and the host DNA. The process of LTR by integrase is performed prior to insertion of the viral genome into the host DNA. Although the transmission is generally via infectious particles, the lentiviruses are capable of infecting the neighbor cells in direct contact with the host cells without having to form extracellular particles. The first clinical trial using a lentiviral vectors are conducted in 2005. The use of lentiviral vectors has been increasingly because the vector system has several attractive features as outlined above. Alpha virus viral vectors. The alpha virus is like a SINB virus, Semliki forest viruses belong to the Togaviridae family of viruses. There are 27 alpha viruses able to infect various vertebrates such as human, rodent, birds, and large mammals such as horses, as well as the invertebrates. The genome of alpha viruses constitute of a single standard positive sense RNA. The alpha viruses are they are of interest to you gene therapy research. The gross research viruses, CNB viruses, Selmiki forest viruses, and Venezuelan equine encephalitis viruses have all been used to develop the viral vectors for gene delivery. The application of replication deficient vectors leads to short-term expressions, which makes the vector highly attractive for cancer gene therapy. The alpha virus vectors carrying the therapeutic or toxic gene used for tumoral injections have demonstrated efficient tumor regressions. There are limitations to the use of alpha virus in the field of gene therapy due to the lack of targeting. However, through the introductions of various antibody domains in a non-conserved loop in the structure of E2, the specific populations of cells have been targeted. Furthermore, the use of whole alpha viruses for gene therapy is of limited efficacy, both because several internal alpha viral proteins are involved in the inductions of apoptosis upon infections, and because of alpha viral capsid mediates only the transmission introduction of mRNA into the host cells. Neither of these limitations extends to alpha viruses enveloped pseudo type of retroviruses or lentiviruses. G. Vaccinia viral vectors. The vaccinia viruses VACV or VV is a large complex involved viruses belonging to the pox virus family. It has a linear double-stranded DNA genome of approximately 190 kilobases in length, which encodes for around 250 genes. The pox viruses are the largest known DNA viruses and are distinguishes from the other viruses by their ability to replicate entirely in the cytoplasm of the host cells outside the nucleus. The vaccine viruses is to use as a tool for delivering the gene into the bacterial tissue, gene therapy, and genetic engineering. Where the viruses like these could be used as a vehicle to carry out good genes into the human cells. First, a scientist would remove the genes in the viruses that cause diseases. Then they would replace those viruses with genes encoded with the delivery effect. For instance, insulin productions in the case of diabetes. Many viruses, many gene therapy clinic trials relies on retroviruses or adenoviruses to deliver the desired genes. Other viruses used as vectors includes adeno-associated viruses, lentiviruses, pox viruses, alpha virus, and herpes viruses. The comparison of different viral vectors in use for gene therapy: genome, genome. Adenovirus is a double stranded DNA. Adeno associated viruses is a single stranded DNA. Alpha virus is a single stranded RNA plus. Herpes virus is a double stranded DNA. Retrovirus or lentivirus is a single stranded RNA plus. And vaccinia virus is a double stranded DNA capsid. Adenovirus is ecosacchedral. Adenovirus associated virus is ecosacchedral. Alpha virus is ecosacchedral. Herpes virus is ecosacchedral. Retroviruses and lentiviruses ecosacchedral, and vaccinoviruses is complex. Quote: adenovirus is naked, adeno-associated virus is naked, alpha virus is enveloped, herpes virus is enveloped, retrovirus and lentivirus is enveloped, and vaccinia virus is enveloped. Viron polymerase is adenovirus is negative, adeno-associated virus negative, alpha virus negative, alpha herpes virus is negative, retrovirus and lentivirus is positive, and vaccinia virus is positive. Viron diameter: adenovirus is 70 to 90 nanometer, adeno associated virus is 18 to 26 nanometer, alpha virus is 60 to 70 nanometer, herpes virus is 150 to 200 nanometer, retrovirus is lentivirus is 80 to 130 nanometer, and vaccine virus is 170 to 200x, 300 to 450 nanometer. Genome size: adenovirus is 39 to 38 kilobase, adeno associated virus is 55 kb, alpha virus is 12 kb, herpes virus is 120 to 200 kb, retrovirus and lentivirus is 3 to 9 kb, and vaccine virus is 130 to 280 kb. Family: adenovirus, adenovirus, adenoviridae. Adeno associated virus is Parvoviridae. Alpha virus is Togaviridae. Herpes virus is Herpesviridae. Retroviruses or lentivirus is Retroviridae. Vaccinia virus is Poxviridae. Infection tropism: Adenovirus is dividing and non-dividing cells. Adeno-associated virus is dividing and non-dividing cells. Alpha virus is dividing and non-dividing cells. Herpes virus is dividing and non-dividing cells. Retroviruses or lentiviruses dividing cells. Vaccinia viruses dividing and non-dividing cells. Host genomes. Adenoviruses non-integrating. Adeno-associated viruses non-integrating interactions. Alpha viruses non-integrating. Herpes viruses non-integrating. Retroviruses or lentiviruses integrating. Vaccine viruses non-integrating. Transgenes expressions. Adenovirus is transient. Adeno associated virus potential long lasting. Alpha virus is transient. Herpes virus is potential long lasting. Retroviruses or lentivirus is long lasting. Vaccine virus is transient. Packaging capacity. Adenovirus is 7.5 kb. Adeno associated virus is 4.5 kb. Alpha virus is 7.5 kb. Herpes virus is less than 30 kb. Retrovirus or lentivirus is 8 kb. And vaccine virus is 25 kb. 2. Non-viral vectors. Beside virus-mediated gene delivery systems, there are several non-viral options for gene delivery. The simplest method is the direct introduction of therapeutic DNA into the target cells. This approach is limited in its application because it can be used only with certain tissues and requires a large amount of DNA. The non-viral method presents certain advantages over viral methods with simple large-scale productions and low host immunogenicity being just two. Previously low level of transfections and expressions of gene held non-viral methods at disadvantages. However, recent advantages in vector technology have yielded molecules and techniques with transfection efficiency similar to those of viruses. The naked DNA. This is the simplest method of non-viral transfections. The clinical trial carried out of intramuscular injections of naked DNA plasmid have occurred with some successes. However, the expressions has been very low in comparison to other method of transfections. In addition to trial with plasmids, there have been a trial with naked PCR product which have had similar or greater successes. This success, however, does not compare to that of other method, leading to the research into more efficient method for delivery of naked DNA, such as electroporations and the use of a gene gun, which shoots DNA coated gold particles into the cell using the high pressure gas lipoplexes and polyplexes. To improve the delivery of new DNA into the cell, the DNA must be protected from the damage and its entry into the cell must be facilitated. To this end, new product, the lipoplexes and polyplexes have been created that could protect the DNA from undesirable degradation during the transfection processes. The plasmid DNA can be covered with lipids in an organism such as myceli or liposomes. When the organized structure is complex with the DNA, it is called as a lipoplex. These are three types of lipids: anionic, negatively charged, neutral, or cationic, positively charged. Initially, anionic and neutral lipids are used for the construction of lipoplexes for synthetic vectors. However, in spite of the fact that there is a little toxicity associated with them, that they are compatible with the body fluid and that was possibly of adapting them to be tissue specific. They are complicated and time consuming to produce, so attention was turned to be the cationic versions. The cationic lipids, due to their positive charge, naturally complex with the negative charge DNA. Also, as a result of their charge, they interact with the cell membrane. The the endocytolic of lipoplexus occurs and the DNA is released into the cytoplasm. The cationic lipid also protects against degradation of DNA by the cells. The most common use of lipoplexus has been in gene transfer into the cancer cells, where the supplied gene have activated tumor suppressor control genes in the cell and decrease the activity of oncogenes. The recent study have shown the lipoplexus to be successful in transfecting the respiratory epithelial cells so that they may be used for the treatment of genetic respiratory diseases such as cystic fibrosis. The complexes of polymers with DNA are called polyplexes. Most polyplexes consist of cationic polymers and their production is regulated by ionic interactions. One large difference between the method of actions of polyplexes and the lipoplexus is that the polyplexus cannot release the DNA loaded into the cytoplasm. So to this end, they go transfections with endosomes lytic agents to lyse the endosomes that is made during the endocytosis. The process by which the polyplexus enters the cell, such as inactivated adenoviruses, must occur. However, this is not always the case. The polymers such as polyethylenamine has their own method of endosomes disruptions, as done cytosine and trimethyl cytosine type of gene therapy. Virtually all cell in the human body contains genes, making them potentially target for gene therapy. However, these cells can be divided into two major categories: somatic cells. Most cells of the body or cells of germline eggs or sperm. In theory, it is possible to transform either somatic cells or germ cells. The gene therapy using the germline cells results in permanent changes that causes a breakdown to subsequent generation. If done earlier in embryonic development, such as during the pre implantations, diagnosis, and in vitro fertilization, the gene transfer could also occur in all cells of developing embryo. The appeal of gene therapy is its potential of offering a permanent therapeutic effect for all who inherit the target gene. The successful germ-line therapy introduces the possibility of eliminating some diseases from a family and ultimately from the populations forever. However, this or raised controversy. Some people view this type of therapy as unnatural and liken it to playing God. Others have concerned about the technical aspects. They worry that the genetic change propagate by the gene therapy may be deleterious and harmful, with the potential for unforgotten negative effect on future generation. The somatic cells are non-reproductive. The somatic cell therapy is viewed as a more conservative, safer approach because it affects only the target cells in the patients and it is not passed on the future generation. In other words, the therapeutic effect ends with the individuals who receive the therapy. However, this type of therapy prevents unique problems of their own. Often, the effects of somatic cell therapy or short-lived because the cells of most tissue ultimately die and are replaced by new cells. The repeated treatment over the course of individuals' lifespans are required to maintain the therapeutic effect. The transporting the gene to the target cell or tissue is also problematic. Regardless of these difficulties, however, somatic cell gene therapy is appropriate and acceptable for many disorders, including the cystic fibrosis, muscular dystrophy, cancers, and certain infectious diseases. The clinicians can even perform this therapy in utero, potentially detecting or treating a life-threatening disorder that may significantly impair a baby's health or development if not treated before birth. In summary, the distinction is that the results of any somatic gene therapy are restricted to the actual patients and are not passed on his or her children. All gene therapy to date on human have been directed at somatic cells, whereas the germline engineering in human remains controversial and prohibited for instance, the European Union. The somatic gene therapy can be broadly split into two categories: ex vivo, which means exterior, where the cells are modified outside the body and then transplanted back in again. In some gene therapy clinical trials, the cells from the patient's blood or bone marrow are removed and grown in the laboratory. The cells are exposed to the viruses that is carried the desired gene. The virus enters the blood and inserts the desired gene into the cell's DNA. The cell grown in the laboratory and are then turned to the patients by injection into the vein. This type of gene therapy is called ex vivo because the cells are treated outside the body. In vivo, which means interior, where the genes are changed in cells still in body. This form of gene therapy is called the in vivo because the gene is transferred to cell inside the patient's body. Gene doping, the gene therapy for restoring muscle lost to age or disease, is poised to enter the clinic, but athletes are eyeing it to enhance the performance. The non-therapeutic use of cells, genes, genetic elements, or the modulations of gene expressions having the capacity to improve athletes' performance is defined as gene doping by the World Anti-Doping Agency, WADA. The analog to gene doping, non-therapeutic application of gene therapy can envisaged in animals for purpose of growth stimulations and improved meat production. For example, growth hormones, myostatin, and anabolic hormones. The gene doping to improve sport performance is not limited to humans, but has also interest in, for example, the sport of horse racing. Risk factors. The concept of gene therapy seems straightforward, but this is clearly an oversimplification. The numerous problems and risk exist that prevents the gene therapy using the viral vectors. The viruses can usually infect more than one type of cells. Thus, when viral vectors are used to carry out genes into the body, they might infect the healthy cells as well as the cancer cells. Another danger is that the new gene might be inserted into the wrong locations in the DNA, possibly causing the harmful mutations to the DNA or even cancer. This has occurred in the clinical trial for X-linked severe combined immunodeficiency (XSCID) patients, in which the hematopoietic stem cells were transduced with a corrective transgene using a retrovirus, and this leads to the development of T cell leukemia in 4 of 20 patients. In addition, when viruses are used to deliver DNA to cell inside the patient's body, there is a slight changes that this DNA could unintentionally be introduced into the patient's reproductive results. If this happens, it could produce changes that may be passed on if a patient has children after treatment. Other concerns includes the possibility that the transfer genes could be overexpressed, producing so much of missing proteins as to be harmful, that the viral vectors could cause an immune reactions, and that the viruses could be transmitted from the patient to other individuals or into the environment. However, the basic mode of gene introduction currently shows much promising, and the doctors and scientists are working hard to fix any potential problems that could exist. They use animal testing and other precautions to identify and avoid the risk before any clinical trial or conducted in humans. Pseudo typing of viral vectors. The viral vectors has a natural host cell populations that they infect most efficiently. The retrovirus has limited natural host range, and although the adenoviruses and adeno-associated virus are able to infect a relatively broader range of cells efficiently, so cell types are refractory to infections by these viruses as well. The attachment to and entry into a susceptible cell is mediated by the protein envelope on the surface of the viruses. The retroviruses and adenoviruses, adeno-associated viruses have a single protein coated their membrane, while adenoviruses are coated with both an envelope protein and fibers that extends away from the surface of the viruses. The envelope protein on with on each of these viruses binds to the cell surface molecules such as heparin sulfate, which localize them upon the surface of the potential host, as well as with the specific protein receptors that either induces entry, promoting structural changes in the viral proteins, or localize the viruses in endosomes, wherein acidifications of lumen anatomy induces this refolding of viral codes. In either cases, the entry into the potential host cells requires a favorable interaction between a protein on the surface of the viruses and a protein on the surface of the cells. For the purpose of gene therapy, one might either want to limit or expand the range of cell susceptible to inductions by the gene therapy vector. To this end, many vectors have been developed in which the endogenous viral enveloped protein have been replaced by either enveloped protein from the other viruses or by the chimeric proteins. Such chimeria would consist into the viron as well as the sequence means to interact with a specific host cell proteins. The viruses in which the developed protein have been replaced as described or referred to as pseudotype viruses. For example, the most popular retroviral vectors for use in gene therapy trial has been the lentiviruses, simian simian immunodeficiency virus coated with the envelope protein G protein from the vesicular somatic viruses. This protein is referred to as a VSV G pseudo-typed lentiviruses and infects an almost universal set of cells. This tropism is characterized of the VSV G protein with which this virus is coated. Many attempts have been made to limit the tropism of a virus vector to one or few host cell populations. This advance would allow for the systemic administrations of a relatively small amount of vector. The potential for off-target cell modification would be limited, as well as many concern from the medical community. Most attempts to limit the tropism have used chimeric envelope protein bearing the antibody fragments. These vectors shows a great promises for the development of a magic bullet gene therapies. Current status of gene therapy research: the Food and Drug Administrations have not yet approved any human gene therapy product for cell. The current gene therapy is experimental and have not proven very successful in clinical trials. Little progress has been made since the first gene therapy clinical trial begins in 1990. In 1999, the gene therapy suffers a major setback with the death of 18-year-old Jesse Gelsinger. Jesse was participating in the gene therapy trial for ornithine transcarboxylase deficiency, OTCD. He died from multiple organ failure for 4 days after starting the treatment. His death is believed to have been triggered by severe immune response to the adenovirus carriers. Another major blow came in January 2003 when the FDA placed a temporary halt on all gene therapy trials using retroviral vector in the blood stem cells. The FDA took these actions after learning that a second child treated in a French gene therapy trial had developed a leukemia-like conditions. Both this child and another who had developed a similar conditions in August 2002 had been successfully treated by the gene therapy for X-linked severe combined immunodeficiency diseases SCID, also known as a bubble baby syndrome. The FDA Biological Response Modifiers Advisory Committee BRMSC met at the end of February 2003 to discuss a possible measure that could allow a few retroviral gene therapy trials for treatment of life-threatening diseases to proceed with the appropriate safeguard. In April of 2003, the FDA eased the ban on gene therapy trial using the retroviral vector in the blood stem cells. Gene therapy and effective treatment for genetic disease. One, a short lived nature of gene therapy. Before the gene therapy can become a permanent cure for any conditions, the therapeutic DNA introduced into the target cell must remain functional, and the cells containing the therapeutic DNA must be long lived and stable. The problems with the integrated therapeutic DNA into the genome and rapidly dividing the nature of many cells prevents gene therapy from achieving any long-term benefits. The patients will have to undergo a multiple round of gene therapy to immune response. Anytime a foreign object is introduced into the human tissue, the immune system is designed to attack the invader. The risk of stimulating the immune system in a way that reduces the gene therapy effectiveness is always a potential risk. Furthermore, the immune system enhances the response to invaders. It has been seen before make it difficult for gene therapy to be repeated in patients. 3. The problem with viral vectors. The viruses, while the carrier of choice in most gene therapy studies, present a variety of potential problems to the patient's toxicity, immune and inflammatory responses, and the gene control and targeting issues. In addition, there is always a fear that the viral vectors, once inside the patients, may recover its ability to cause diseases. Fourth, multi-gene disorder. The conditions or disorders that arises from the mutation in a single gene are the best candidate for gene therapy. Unfortunately, some of the most common occurring disorders such as heart disease, high blood pressure, Alzheimer's disease, arthritis and diabetes are caused by the combined effect of variations in many genes. Mutagens or multifactorial disorders such as these could be especially difficult to treat effectively using the gene therapy. Ethical consideration for using the gene therapy. 1. What is the normal and what is a disability or disorder, and who decide? 2. Or disabilities a disease do you need to cure or prevent? 3. Does searching for a cure demands the life of individuals present affected by the disabilities? 4. In somatic gene therapy, which is done in adult cells of persons known to have disease, more or less ethical than the germline gene therapy, which is done in cell and sperm cells and prevent the trait from being passed on the few further generations. In case of somatic gene therapy, the procedure may have to be repeated in future generation. 5. The preliminary attempts to gene therapy or orbitally expensive. Who will have access to these therapies? Who will pay for their use? A new gene is inserted directly into the cells. A carrier called vector is genetically engineered to deliver this gene, and adenoviruses introduce the DNA into the nucleus of the cells, but the DNA is not integrated into a chromosomes. Questions: which of the following viruses is not used in gene therapy? Papilloma viruses. Answer: some of the viruses currently used in gene therapy includes retroviruses, adenoviruses, adeno-associated viruses, and herpes viruses. Question: the common gene delivery system for in vivo gene therapy is adenoviral vector. 3. Which of the method is useful, especially in the treatment of cancer? Adenoviral vector.